Hello, everybody, and welcome to episode 4 of our Building with Blitz series. We're diving into Loading 301 from our loading series. This will probably be the last series for loading for a second before we dive into some example problems. But this episode is titled Moving and Shaking because we're going to be diving into seismic and wind force analysis and kind of the design practices that go into some of those procedures. So why should we care? Wind and seismic forces are the primary forces for lateral force design. This is the design of the main lateral force resisting system. This is kind of the fancy structural term for the structure that resists lateral forces. Basically, kind of self-explanatory there. But in certain structures and geographies, lateral forces can dictate the entire design. What this means is that, like in the coast, and so using the southeast, I'm based out of the southeast, so like along the Gulf, Florida, for example, I have a good friend who works in the crane foundation design kind of area, and wind speeds in, say, Orlando, Fort Lauderdale, and as you get closer, like Miami, can get pretty high, up into the 140 plus mile an hour range. That's a lot of lateral load just from wind. And as we know, in California, seismic forces dictate the design so much that in order to become a licensed engineer in California, they have a specific seismic exam that you have to take, which is interesting. And another interesting piece for seismic design is that for our southeast viewers, Memphis is actually a pretty high seismic area, which you don't normally think about. You normally think when earthquakes, you're thinking, oh, out in California and things like that. But Memphis and kind of the Western Tennessee region has some pretty high seismic activity as well. So let's go ahead and dive right in. So we'll start with wind analysis. This is going to cover one procedure for wind analysis. This is a directional procedure. You can, it's kind of the main analysis procedure for coursework and for licensure exam, which is why I'm kind of going over it here. So in ASC 722, it should be noted that ASC 716 is what is used on the licensure exam. The chapters are still the same. I just happen to have 722 in front of me as I was making this PowerPoint. So we start with chapter 26. This is kind of the general requirements for wind loading. And then chapter 27 is the directional procedure. And then another important chapter is chapter 30. This is components and cladding. There could be some one-off questions about cladding or a component on a structure. I'm pretty sure an example of this could be like a highway sign would be chapter 30, but I do know like a rooftop components, like a HVAC system or a big, RTU. If you have a question on that falls under chapter 30. So chapters 26 through 31 cover the entire wind analysis kind of section for ASC 7, but these are the three that you'll probably be focused in on during licensure exam preparation and coursework. So the general requirements, the enclosure classification is important. This is defined in chapter 26, and it's a proportion of area of openings to the total area of wall face. So an example of this would be if you have a wall that is mostly windows or mostly doors, what have you, that is going to be classified as a partially open or open, quote, enclosure. Whereas if you have just a flat, wall with no openings, that's an enclosed classification. There's a little bit more nuance to it, but if you have 80%, roughly 80% wall and less than 20% opening, then your enclosure is going to be partially enclosed. This, again, is outlined in Chapter 26, and there are some rules as if you have opening greater than 10% of the total wall area, then that changes the enclosure classification, as well as if you have multiple openings of a certain proportion, then that changes the enclosure classification as well. But it is important to note, like if you're designing, for example, a canopy structure for a park, for example, that is going to be a different enclosure classification than a typical building. So it's important to check. And then you have your wind speed maps. This, it depends on the risk category of the structure, which is defined in Chapter 2 or Chapter 1 of ASCE 7. This risk category is basically what if this structure fails, what risk does that pose to the general welfare of society? An example of this would be a level 1 trauma center hospital. That is a risk category 4 because if that hospital collapses, that is going to have catastrophic effect on society. A nuclear power plant, for example, if that fails, that is a big for the surrounding population, which would make it a risk category 4. A risk category 1 is your backyard shed. Yeah, you might lose your lawnmower, but that's not going to really hurt the general populace. So the higher the number of your risk category, the more important it is. And so now moving forward to kind of specific of how the wind affects your structure, directionality factor. This is dependent on the building geometry, what type of roof you have, how the building is kind of oriented, or the layout of the corners of the building. Mostly it's dependent on the roof. So if you have a dome roof, for example, that's going to be a little bit different than a low slope roof as far as what wind pressure you're going to put on your structure. The exposure category, I said it's dependent on the building location relative to the space around it. This is meaning if you have a building with nothing around it, there's nothing to break up the wind itself. Meaning that you're going to have a different exposure category listing versus a building with a bunch of stuff or trees around it, because you're not going to get as much wind per se on the structure itself. So there are exposure categories A, B, and C, I want to say, and that is dependent on where the building is and the characteristics of the surroundings of the building. And then you have topographic and ground elevation factors. These kind of go hand in hand because if you have a building on the face of a hill, on the top of the face of a hill, you're going to get different wind effects than if the topography of the surrounding area of the building is flat. So there are factors to account for that. As in ground elevation, this is from sea level. If you get different wind speeds based on where you are elevation-wise. So this factor also accounts for that. And these can be also dependent on exposure category and risk category. So it's important to include all the factors when you have to, but while you're doing kind of your desk study of your wind speeds or your wind forces, go ahead and get all the factors beforehand instead of saying, oh, let me just work on directionality factor and then I'll go to ground elevation factor later. Get all of them beforehand so that way you have all your bases covered. So let's get into velocity pressure. This is still in chapter 26, but is used in chapter 27 as well. So this graphic, I was told that I needed to include more graphics in my videos. So I had my good friend, Mr. Claude, develop this velocity pressure graphic. And this formula at the top, the Q sub Z, is the pressure in pounds per square foot. And you have your constant of 0.00256. That does not depend on any factor. You're going to use that in every velocity pressure calculation that you run. So then you have your exposure coefficient. So your exposure category here is B, C, or D. And as you can see, kind of the explanation below each exposure category, B is urban, suburban, C, open terrain or scattered obstruction, and then D is flat or open water or coastal. So like if you're building a beach house, your exposure category is going to be D for wind. Topographic factor is most of the time conservatively left as 1. Directionality factor, unless you have some geometry, some kind of funky geometry, is most of the time going to be 0.85. And then the wind speed is just from the map, or it could be given to you in the problem statement, or from the ASC hazard map, which we can make a separate video on later. But the wind speed is squared. So you'll plug in that equation, and this is kind of an example of your height factor, all these things plugged in. And then the bottom here is the velocity pressure of roughly 30 pounds per square foot. And that's just from kind of plugging and chugging that equation. So the first step here is to get the velocity pressure, and then you can move on to the directional procedure. So this is kind of an overall breakdown of really starting it from the top. So step 1 is risk category. This is what I was talking about before, like a hospital or your backyard shed. Mr. Claude, again, used the International Building Code, which is okay. They're the same as far as ASCE 7 or IBC. So you'll determine your risk category. Then you'll determine your basic wind speed, wind parameters. This is going back to the directional or the topographic factors. You'll plug that into the velocity pressure. The gust factor is in chapter 26 again, and this most of the time is going to be 0.85 for rigid. If you have flexible diaphragms or flexible members within your lateral force resisting structure, you're going to do some additional calculations, but there's a table for it. And then you'll get your pressure coefficients. This is positive and negative, depending on if you're examining the windward wall, leeward wall, or the side walls. And then you'll have your design wind pressure. So you'll get your velocity pressure, you'll have your gust factor and your pressure coefficients. Then you'll plug that in, get your design wind pressure, and then you'll get your minimum wind load. So there are some minimums defined by ASCE 7, 16 pounds per square foot. Most of the time you're going to get over that, especially for windward walls. And then your final kind of deliverable will be your minimum wind load plugged into your load combinations for your design. And most of the time, this is idealized as a line load on the diaphragm of each of the corresponding level to the height of the structure. But there are different ways you can do it. So this is kind of a rough sketch. Again, Mr. Claude did this for what a pressure diagram would look like. So we have the windward wall outlined in red. This is the direction that we're assuming that the wind is going to be blowing. And an interesting thing about wind is that it's based on 3-second gust speeds. So we're assuming that, going back to the previous example from the calculation of the pressure, it's 115 miles per hour, 3-second gust. So we're applying that to the windward wall. We're getting a pressure for the windward wall. We're also getting a suction against the leeward wall. This is kind of follows some aerodynamics practices and principles, but just know that your windward wall, it's going to be pushing against the wall. The leeward wall is going to be kind of a suction pulling the wall out of plane, but in the direction of the wind. And then for roof, you're going to get an uplift force. This is also kind of it's a negative pressure, so it's a suction force kind of acting to pull the roof away from the structure. And you can see that in the diagram. So now that we've done our wind, let's move to the seismic analysis. And this is a very, very large part of ASCE 7. It is seismic analysis. While you can piece it together, there are chapters 11 through 21 of ASCE 7 outlining different analyses and practices for seismic design. For this video, because you could talk forever about wind. You could talk for double forever about seismic. So for this video, we're going to be focusing on chapters 11 and 12. 11 is the seismic design criteria. This is kind of site-specific, ground motion values, and then moving into chapter 12, which is equivalent lateral force procedure and kind of the design requirements for buildings. So chapter 11 is kind of the starting point. You get your site classification, your seismic design category, and ground motion values, as far as your fundamental periods, and your things like that. And so here, importance / risk category matters because that will depend on what you assign for your seismic design category. And there are restrictions for seismic design categories, with F being the kind of most restrictive. That's you have restriction at building height, certain building systems you're not allowed to use for kind of, I guess, more in-depth seismic design categories. So it's important to determine that up front because you are limited in what you can do if you are building in a seismic heavy area, or your problem statement is focused on seismic heavy criteria. So that's very important to determine at the beginning. So Mr. Claude again gave us a flow of chapter 11 and kind of what you kind of go through. Similar to wind, risk category is you can't really operate or design a structure without determining the risk category first. So that's always a good step one. From there, the site classification, this is based on the type of soil or rock that the site is composed of. So if you have kind of low plasticity dirt, or you have primarily large aggregate-based rock, or things like that, that will affect your site classification. Then you have your mapped accelerations. This comes from the ASCE hazard map. Is a very good tool to use. You can't use it on the licensure exams, but in practice or during class coursework, you most of the time can use it. Very good kind of resource. I'll link that in the description below, just kind of if you're not familiar with it. So site coefficients, and then you have your spectral accelerations. This comes from chapter 21 as well. This is dependent on, and this can get pretty complicated, but long story short, this depends on the rate at which you're designing for the ground motion values. So you have your site coefficients, which is kind of how your site is going to behave. And then you have your accelerations, which is how fast your site is going to accelerate under seismic excitation. This depends, again, on location. And then you take your design accelerations from your spectral accelerations, and then you kind of have your what movement values you're going to design your structure for. So then you take that, and then you get your response spectrum. This is based on your period and the different frequencies at which your structure is going to oscillate or vibrate depends on the period response of that structure. So a stiff structure such as a steel moment or a concrete frame is not very ductile. So you're going to have very low vibration period because you don't have a lot of ductility within that structure. A steel frame is a little bit more ductile or a lot more ductile than a concrete frame. So you're going to have a difference in the period at which you're going to design that structure for. Like I said, this can get very complicated, and there's actually a lot of study being done to kind of incorporate different periods and frequencies of different structures and how that interacts with the system. But just so you know, you get a value and you design for that period. Then you use all that to determine your seismic design category, A through F, with restrictions being placed as you get further into the category, with F being the kind of most severe, quote unquote. So then step 9 is your analysis of equivalent lateral force. So what we want to get out of this is seismic design requirements. The type of structure determines the R value. This is your seismic response modification factor, where if you have a high R value, such as ASC 722, for example, outlines a special steel moment frame as a value of 8. This means that because you're dividing by this value, you're decreasing the seismic force that's being applied to your structure. If you have spitball in here, but a wood diaphragm, that's going to be a pretty low R value, such as like 1, 1.5, or 2. You're going to have more lateral force because your frame itself has a lower response factor, meaning that it can't distribute those lateral forces as well because it's not designed for it. A special steel moment frame is specifically designed to handle lateral force, which means it's going to have a higher modification factor. I mean, it's just intuitive there. And then section 12.3 is structural parity, irregularity, and diaphragm flexibility. This is important. If you have a horizontally irregular structure, you have to do some funkiness or certain caveats. You have to put a little bit more mass or distribute the forces a little bit differently. So it's important to check whether you have irregularity. This comes from the plan kind of geometry of the structure. For licensure examinations, you might get a question based on, is this structure irregular? Not so much as, this structure is irregular, let's do XYZ analysis to it. So kind of put that section 12.3 in your back pocket, just to, if you get to say, hey, is this horizontally irregular or not, you'll be able to determine that. So vertical distribution of seismic forces, ELF is equivalent lateral force procedure. This is, we've done our analysis for our ground motion. We've gotten kind of how we're going to predict our building. is going to behave and accelerate and vibrate and do all the moving and shaking. So we need to quantify that and distribute that that lateral force vertically along the building height. So we do that by equivalent lateral force procedure. This is kind of a fancy way of saying the lateral forces are distributed along the levels or heights of the structure proportion to each level's weight and height from the ground. Meaning if you have a 1,000 kip floor that's 20 feet above the ground floor, you're going to distribute that according. And if you have on that same building a 1,500 kip floor that's 20 feet or 30 feet above the ground, that's going to get more because you have a greater proportion of height and weight relative to the total height and weight of the structure. And what does that mean? So the seismic weight of your structure is determined by section 12.7.2 of ASE 7. This can be the dead load of the structure. You're going to include all of that. 20% of storage load for designated areas. This can be considered like a library stacking area is considered storage, or a like an ASRS storage for like a tire storage area. If you have a tire plant, I'm saying that because I help work on a tire plant, or a Coca-Cola distribution center. You have storage for all the Cokes and Dr. Peppers and whatever. You're going to use a quarter of that load. Partitions, this is bolded because the Ninja has come back. You have to include, if you have partitions, you have to include 10 pounds per square foot of that load. So again, you can't reduce it on live load, and it's sneaking back up for seismic weight calculation. Permanent equipment, this can be considered an RTU on a rooftop, or like a bridge crane, monorail crane, just any kind of permanent equipment for like an industrial use case or whatever. Heavy snow, this is 45 pounds per square foot on what's considered to be a flat roof. If you are snowing and you have an earthquake, that is interesting, and yeah, you need to design for that. Because if you don't, that's not good. Roof gardens, fluid or bulk material storage, this can kind of go to industrial use case as well. So the equivalent lateral force summary here, we have our system parameters. Again, we have our R value and our importance factor, as well as the CS. This is the seismic response factor. Not the seismic response factor, excuse me. It's the seismic response coefficient. This is determined in proportion to the fundamental period of the structure and some site criteria. You're going to multiply this by the seismic weight to determine the base shear, which is that V value. And then you're going to determine, you're going to split that up dependent on the proportion of the height and weight of the structure to get a lateral load proportion to each level. So the FE exam, you're going to have limited questions on this topic. It might be something a little different or what have you. And then, okay, so like I was saying, limited questions on this topic for the FE exam. For the PE exam, you're going to get a little bit more in depth. As I've stated previous, you're going to get between 12 to 18 questions just on loading. And there are going to be some code gotchas. An example of this is the 100% and 30% orthogonal loading. I specifically remember this question from either, I don't think it was actually on the exam, but it was during the preparation. This is in section 12.5.1.2 of ASE 7. And again, this is determined based on the seismic design classification, or the criteria, or the seismic design class. If you have certain effects of the irregularities or certain things like that, you actually apply 100% of your seismic force in one direction, and then you combine that with 30% of the force for the perpendicular direction of the axis you are designing for. So you actually have 130% of your lateral force in an area, depending on the building geometry and some other direction of loading procedures, again outlined in ASCE 7, chapter 12.5. And there's other things like that for the seismic. Because there's so many chapters, it's important to, a way to kind of get around this is to just have a lot of practice questions. You could know the code back and forth, but that's really going to be a waste of time, in the sense that you're not going to get a whole lot of like nonlinear time history analysis questions, if any, things like that. So you kind of have to be smart about how you're studying the code to go over those gotchas, but there are some out there. And this will be talked about as we expand into example problems and things like that. So for the next episode, I think we're going to take a break from the loading series, and go to mechanics. So we're going to start with Mechanics 101. This will be stress, strain, and internal forces of a member. And yeah, I look forward to getting started with this. And then some example problems will be posted soon. I have to get some kind of tablet or way to write to be able to kind of write out those problems. So for now, we're going to keep going with the concepts, but example problems are on the horizon. So yeah, thanks for listening, and have a great day.